So far in this class, we've talked about how to find the derivatives for the sum of functions, for the difference of functions, for the product, and for the quotient of functions. So at this point, we just want to continue building our repertoire of functions that we can take derivatives of. So in this video, we're going to go over derivatives for a composition of functions. And in this example, we'll be using the function tan of x squared. So before we get started, I just want to say that it's really important to be able to differentiate when we have a composition of functions versus a product of functions. So note, tan of x times x squared is different than tan of x squared. And the way I differentiate these functions in my head is I like to think of a composition of functions as kind of a matryoshka doll, one of those Russian dolls, where when you take off the top of one of the dolls, you have a smaller function within it. And so in this case, we have x squared is inside the function of tangent of x. So that's the first step in recognizing when we're taking a derivative, is something a product, in which case we'd use the product rule, or something a composition of functions, in which case we're going to be introducing the chain rule for this example. So now that I know I have a composition of two functions, I have to ask myself, what are these functions and what are the derivatives that I know? So at this point, I know that the derivative of tangent of x is equal to secant squared of x. But in this case, I have a slight difference. I have a composition of x squared within the tangent function. And so what I can do is I can rewrite this where I'll say, let u equal x squared. I'm going to be rewriting my inside function as a placeholder with a single variable. So then when I'm taking the derivative of the tangent of x squared, instead of taking the derivative with respect to x, I'll be taking the derivative with respect to u, since that's what I use as my placeholder. And I have the derivative with respect to u of tangent of u. And this I know how to take the derivative of. However, because I am using u as a placeholder for my inside function, I would then also have to take the derivative of that inside function, which was x squared. So at this point, I can take the derivative. The derivative with respect to u of tangent of u is secant squared u. And then the derivative of u with respect to x of x squared is the same as 2x. So all I have to do here for the last step is I want to rewrite my derivative function so that everything's in terms of x. And since I let u equal x squared, I have that in general, the derivative of tangent of x squared is equal to 2x times secant squared of x squared, since that's what u is representing. So this process of finding the derivative for a composition of functions has a name, and that name is the chain rule. So even though we've just done one small example here, I'd like to give you the general formula. In general, if we have a function f that's composed with an inside function g of x, and we're taking the derivative of the entire composition, this is equivalent to the derivative of the outside function at the inside function, and then times the derivative of the inside function. And if you're interested in seeing an example where I use the chain rule multiple times with a more complex function, go ahead and watch the next video of mine.